Hello students, myself Dr. Himmat Singh from School of Pharmacy, Suresh, Gyan, Vihar University, Jaipur. In physical pharmacy, today we have to discuss about the unit viscosity and rheology. In this unit, the topic of today's concern is non-Newtonian systems, pseudoplastic system, dilatant systems, and plastic systems. So, the objective of today's lecture is to know about the what is Newtonian systems and then what is non-Newtonian systems. Then classification of non-Newtonian systems. Then description about the pseudoplastic systems, dilatant systems, and description regarding the plastic systems. Then we have to discuss about the examples of different types of non-Newtonian systems. And the learning outcomes of today's lecture is students may be able to know after completion of today's lecture about the non-Newtonian systems, classification of non-Newtonian systems, description regarding the pseudoplastic systems, dilatant systems, and plastic systems, and then different examples regarding the non-Newtonian systems. So, as we discussed in our previous lecture, what is rheology and what is viscosity? So, again, we can summarize the definitions or introduction regarding the rheology, and then we have to discuss about the different non-Newtonian systems. So, let us start from the rheology. So, it's we know about the rheo means flow and logy means science. So, rheology is the science or physics that concerns with the flow of liquids and the deformation of solids. It is not only related with the flow of liquid, but it is also related with the deformation of solids. Study of flow properties of liquids is very important for pharmacists working in the manufacture of several type of dosage forms. Either it may be liquid dosage form like the solutions, emulsions, suspensions, etc. Or it may be semi-solid dosage forms like gels, ointments, cream, paste, etc. So study of flow properties of liquids, especially in the case of different type of semi-solid dosage forms and liquid dosage forms are very important for a manufacturing pharmacist. These systems change their flow behavior when exposed to different stress conditions. So when we apply the different stress or different variation in temperature, pressure, etc. So their flow behavior can be changed. Then when we discuss about the fundamentals of rheology, so as we discuss, rheology is the science or branch of science which is related with the liquid flow or deformation of solids. So some fundamental aspects of rheology are given here. Manufacturing of dosage forms, like materials undergo process such as mixing, flowing through pipes, filling into the containers, etc. Or flow related changes influence the selection of mixing equipment. So regarding the manufacturing or formulation of any type of dosage form, there are different type of unit operations which may be conducted in a manufacturing industry. So it contains like the mixing, flowing, filling into the containers. So there are so many unit operations or unit process which depends on the flow property. So it shows the significance of rheology itself. Then handling of drugs for administration. So the syringeability of the medicines, the pouring of the liquids from the containers, extrusion of ointments from the tubes. So all these type of depends on the changes in the flow behavior of the dosage form, especially in the case of topical dosage form or transdermal dosage forms and liquid dosage form. So handling of drugs for administration depends on the aspects of rheology. So when we go through the broad classification of rheology on the behavior of different liquids, they can be classified as Newtonian, and second one is the non-Newtonian. So based on their different characteristic features and flow ability or flow properties, the rheology can be divided in two types. One is the Newtonian behavior, and second one is the non-Newtonian behavior of the liquids. So now, what is Newton's law? So as we already discussed in previous lectures about the Newton's law or Newtonian liquids. So just we have to summarize the Newton's law of flow. So according to Newton's law of flow, higher the viscosity of a liquid, the greater is the force per unit area. So force per unit area, which can be known as shearing stress, or it can be denoted by capital F. So where the greater force is required to flow a liquid, it means the liquid having more viscosity. So higher the viscosity of a liquid, the greater is the force per unit area required to produce a certain rate of shear. So shearing stress, which can be denoted by capital F, it is the F by A or F dash by A, force per unit area, and shear rate or rate of shear is dV by dr. So dV is the difference in the velocity and dr is the distance. So when we compare with the stationary plate and then other plates, when we compare or when we assume a liquid consisting of different type of layers, one is the stationary layer which is situated at the bottom part, or other layers which move with the velocity v. So when we apply the force per unit area, which is known as shearing force or shearing stress F by A, it can produce a certain rate of shear, which the velocity can be changed as per the distance. So as per the Newton's law of flow, rate of shear is directly proportional to shearing stress. So when we apply the more shearing stress, there will be the more rate of shear. So as per the Newton's law of flow, rate of shear is directly proportional to the shearing stress, where F is equal to eta G. So F is the shearing stress here, and G is the rate of shear. Eta is the viscosity or viscosity coefficient. So where shearing stress can be denoted by F dash by A, force applied per area F by A, and G is the dV by dr, difference in the velocity, and dr is the distance from the different stationary layer to the different layers. So as per the Newton's law of flow, F equal to eta G, rate of shear is directly proportional to shearing stress. When we apply the force per unit area, there will be the change in the rate of shear. And as per the Newton's law, the change in the rate of shear is directly proportional to the force per unit area or shearing stress. So Newtonian and non-Newtonian flows can be again divided as Newtonian flow and non-Newtonian liquids. So on the basis of Newton's law of flow, we can classify the different fluid into two types, like the Newtonian liquids, and another one is the non-Newtonian liquids. So there are two types of flow also, Newtonian flow which obey the Newton's law of flow, and second one is the non-Newtonian flow which do not obey the Newton's law of flow. So before starting the non-Newtonian flow, non-Newtonian behavior of liquid, just we have to understand the Newton's law of flow, and the liquid which obey this Newton's law of flow is per the Newton's law of flow, where the rate of shear is directly proportional to the shearing stress. So F equal to eta G, as we discussed in previous slides. So Newtonian flow, this Newton was the first to study the flow properties of liquids in quantitative terms. Liquids that obey this Newton's law of flow are called as Newtonian liquids. So Newtonian liquid means when we plot a curve which is known as rheogram or consistency curve. So when we plot a curve, the rate of shear and shearing stress. So when we apply the shearing stress on x-axis and when we plot the graph on diagram on the based on the behavior of different liquids, if the rate of shear and shearing stress are directly proportional, then we can say that the Newtonian liquid is this type of liquid is we show the Newton's law of flow and it is called as Newtonian liquid. So F equal to eta G. So when we plot the graph between the G, this rate of shear and shearing stress, we can obtain a straight line. It indicates that our sample is obeying the Newton's law of flow and it is classified as Newtonian type of liquid. So in liquids that obey Newton's law of flow, they are called as Newtonian fluids or Newtonian liquids. And this is the characteristics rheogram or consistency curve for Newtonian type of liquids. So a Newtonian fluid named for Isaac Newton is a fluid whose stress versus rate of shear curve is linear and passes through the origin. So as we already seen in our graph or rheogram, this is the rate of shear and shearing stress. When there is a straight line between the rate of shear and shearing stress, it passes through the origin. So it is the characteristic rheogram or consistency curve for Newtonian fluid where the curve is linear and passes through the origin. The constant of proportionality is known as the viscosity. So viscosity is resistance to flow. More resistance to flow means the liquid will having the more viscosity. Less resistance to flow means less viscosity. So the constant in this equation for Newton's law of flow is known as viscosity coefficient or viscosity. Examples of these type of Newtonian flow or Newtonian liquids or liquids which obey the Newton's law of flow is called as Newtonian liquids like water, chloroform, castor oil, ethanol, etc. The viscosity of these type of liquids can be measured by very simple instruments like the capillary viscometer, like Oswald viscometer in laboratory. So with the help of Oswald viscometer or capillary viscometer, we can measure the viscosity of these type of Newtonian liquids. Then viscosity, as we discussed, it is defined as the resistance to the flow. And eta is the coefficient of viscosity. It is calculated as eta equal to F by G. When we rearrange the Newton's law of flow equation, we can obtain the value of coefficient of viscosity, and it is commonly known as viscosity. It is given as F by G, where F is the shearing stress and G is the rate of shear. So viscosity coefficient can be defined or can be represented by this equation eta equal to F by G. So eta means viscosity or viscosity coefficient or coefficient of viscosity will be shearing stress divided by rate of shear. And when we see the example of shearing stress with the units like F equal to F by A, means unit of F is the force, means the dyne, and A is the square centimeter. So dyne per square centimeter is the unit of shearing stress, and when we go through the rate of shear, it is dV by dr. V is the velocity, so centimeter per second, and R is the distance. It can be represented in centimeters in CGS system. So when we combinedly give the unit of viscosity, it will be the poise or dyne into second per square centimeter. So it can be commonly represented in terms of poise or centipoise. So 100 centipoise equal to 1 poise. So poise is the very common unit which can be used in representation of viscosity. Now in non-Newtonian flow, so the liquids or the samples which show the Newton's law of flow can be classified as Newtonian liquid, whereas the sample or liquid or fluid which do not obey the Newton's law of flow, they can call as non-Newtonian liquids, and the behavior of these type of non-Newtonian liquid can be shown as non-Newtonian flow behavior. So a non-Newtonian flow is defined as one for which the relation between the F and S is not linear, where F is the shearing stress and S is the rate of shear. So it can be represented by G also. So a non-Newtonian flow is defined as one for which the rate of shear and shearing stress is not directly proportional, and we cannot obtain a linear graph as we obtained in our Newtonian fluids. In other words, when the shear rate is varied, the shearing stress is not varied in the same proportion. The viscosity of such a system thus varies as the shearing stress varies. So shearing rate is in case of non-Newtonian flow, it is the condition when the shear rate is varied or changed, the shear stress is not varied or not changed in the same proportion as we discussed in our Newtonian fluids. The viscosity of such a system thus varies as the shearing stress changes. It can be seen in liquids and in solid heterogeneous dispersions like the different types of emulsions, suspensions, colloidal dispersions, and ointments. So these are the different examples of non-Newtonian behavior or non-Newtonian flow behavior, which can be seen in different type of liquids or in solid heterogeneous dispersions like emulsion, suspension, colloidal suspension or colloidal dispersions, and different type of semi-solid diffusions like ointments. And when we go through the non-Newtonian flow, non-Newtonian bodies are those substances which fail to follow Newton's law of flow, like the liquid and solid and heterogeneous dispersions, as we discussed with different examples. So now the Newtonian fluids are defined as the substances or liquids or fluids which obey the Newton's law of flow. And non-Newtonian liquids or non-Newtonian fluids are the substances which do not obey the Newton's law of flow. And when we classify the non-Newtonian liquids, there are three broad types or three classes of the non-Newtonian liquids, like the plastic liquids, pseudoplastic liquids, or dilatant liquids. On the basis of their flow behavior, they can classify it into three types of flow: plastic flow, pseudoplastic flow, and dilatant flow. When we go through the different consistency curve or rheograms of different liquids, we can compare all different types of liquids as given in this slide. You can see here where A diagram or A rheogram show the Newtonian flow, where the rate of shear and shearing stress is directly proportional. You can obtain a linear curve for shearing stress and rate of shear when plotted on a rheogram. In curve number B, where the rheogram show that there is no linearity, it can be obtained after the yield value, which can be represented by small n. This type of liquid is known as simple plastic liquids, or flow is known as simple plastic flow. And C rheogram number third, which is the representation of pseudoplastic flow, where the curve is not linear, which is plotted between again rate of shear and shearing stress. And number four, this is the characteristic rheogram for dilatant flow, which is just inverse to pseudoplastic flow. So there are different types of liquids or different type of flow behavior based on the Newton's law of flow, or which do not obey the Newton's law of flow. So now let us discuss non-Newtonian flow or non-Newtonian liquids one by one in details. So in non-Newtonian flow or non-Newtonian liquids, we can obtain the characteristic rheogram for each and every system. First, we have to discuss about the plastic system or plastic flow. So plastic flow is the very simple type of non-Newtonian flow. And you can find when we plot a rheogram between the rate of shear or shearing stress, we cannot obtain a linear line. So the characteristic features of this type of plastic flow, so the curve or rheogram does not pass through the origin. It intersects the shearing stress axis or will if the straight part of the curve is extrapolated to the axis. So when we extrapolate this line to the shearing stress, it cut at a specific point, and this point is known as yield value. So this is the characteristic rheogram for plastic flow, where the curve does not pass through the origin and it intersects the shearing stress axis at a particular point, which is referred to as yield value and can be represented by small f. So this is the characteristic diagram of plastic flow. So in this type of plastic flow, in which curve does not pass through the origin, the substance behave initially like the elastic body, and it fails to flow when less amount of stress is applied. As increases the stress leads to non-linear increase in shear rate, but after that curve is linear. So after a certain shearing stress is applied, the line may be following the linearity. So as increase the stress, it leads to non-linearity, but it increase in shearing rate, but after curve is linear. And the linear portion extrapolated intersects the x-axis at the point called as yield value. So plastic flow shows the Newtonian flow above this yield value. So above the yield value, when we apply the shearing stress, the liquid or system behave like the Newtonian flow, where the rate of shear will be directly proportional to the shearing stress. So this is the characteristic point which is known as yield value for plastic system. These are also known as Bingham bodies. The owner of Bingham, which is the pioneer of modern geology, is known as Bingham bodies. So plastic bodies or plastic systems are also known as Bingham bodies. So the curve represents plastic flow. So these type of materials are called as Bingham bodies. Bingham bodies does not flow until the shearing stress is corresponding the yield value exceeded. So once the yield value is exceeded, then the Bingham body will be show the behavior like the Newtonian type of liquids, where the shearing stress rate of shear will be directly proportional to each other. So yield value is very important property of certain type of dispersions, and the reciprocal or reverse of the mobility, as we discussed earlier, is the known as plastic viscosity. So the reciprocal or inverse of mobility is known as plastic viscosity. Examples of this type of plastic behavior like the zinc oxide in mineral oil, certain paste, paints and ointment type of preparations. So mineral oil, certain paste, paint and ointment type of preparation can show the plastic type of behavior. And why it shows that it can be explained like the plastic flow explained by the flocculated particles in concentrated suspensions, ointments, paste, and gels. And due to the aggregation of these particles, there is a weak physical force which is known as van der Waals force, which is responsible for aggregation of these particles or formation of flow. So when we apply the force per area shearing stress, the flocculated particles will segregate and they can disperse. So the individual particles can be segregated after applying the particular shearing stress regarding the yield value. So when we apply the external force, we can segregate the particles, and when we increase the stress, they can show the flow behavior like the Newtonian type of liquids. So the curve for the plastic flow is as follows, like the rate of shear and shearing stress. When we plot the graph, as we already discussed, this is the non-linear graph, but after a certain point, the graph show the linearity. So this point is referred or known as yield value. And when we apply the shearing stress corresponding to the yield value, again there may be linearity in the graph. So this is the characteristic curve for the plastic flow, where the slope is equal to the mobility. So when we compare this graph or this curve or rheogram with the straight line equation, which is y equal to mx plus c, and it can be converted into the logarithmic equation. Then when we convert it, we can obtain the value of mobility from the slope of this graph. So the equation describing plastic flow is slightly changed from the Newtonian behavior. Like the plastic viscosity can be represented like U equal to capital F minus small f divided by G, where F is the capital F is the shearing stress, and small f is the yield value, and G is again rate of shear. It's dV by dr. Rate of shear is equal to the depends on the velocity changes with the distance. So plastic viscosity can be described by this equation U equal to F minus small f divided by G, where small f is the yield value. Now when we go through the second type of behavior of non-Newtonian systems, this is known as pseudoplastic flow. So the system are known as pseudoplastic system. So this is the second type of non-Newtonian system. So after the discussion of Bingham bodies, which is known as plastic bodies or plastic system, we have to discuss about the pseudoplastic flow or pseudoplastic behavior of different materials. So the curve for the pseudoplastic material begins at the origin. So you can see in this diagram, the rheogram is given here. When we plot the rate of shear and shearing stress on this rheogram, so shearing stress on x-axis or epsica on rate of shear on ordinates, so we can obtain a characteristic rheogram for this type of pseudoplastic systems. So the curve for this pseudoplastic materials begins at the origin or at least approaches it at low rate of shear. So this is different from the plastic flow where the yield value was the characteristic point of the plastic behavior, and the pseudoplastic behavior where the curve approach or curve begins at the origin or at least approaches it at low rate of shear. You can find the curve thus the origin from this rheogram. The curved rheogram for this pseudoplastic material is the characteristic rheogram for pseudoplastic behavior. It is due to the shearing action on the long chain molecules of materials such as linear polymers. So examples of this type of behavior or this type of systems are the long chain molecules of materials like the linear polymers, and the curve is known as rheogram for pseudoplastic flow. So this is the curved rheogram, which is the specialty or characteristic features of pseudoplastic materials, and it is occurs due to the shearing action on the long chain materials like the linear polymers. Many pharmaceutical products like liquid dispersions of natural and synthetic gums, which is also known as hydrocolloids, high molecular weight substances, and they are generally used as viscosity imparting agent in pharmaceutical formulations. So liquid dispersions of natural and synthetic gums show the pseudoplastic flow. They are classified as pseudoplastic systems. An example of these type of systems are like tragacan in water, sodium alginate in water, methyl cellulose in water, or sodium carboxy methyl cellulose in water. So different liquid dispersions of either natural or maybe synthetic gums are the examples of the pseudoplastic behavior or pseudoplastic systems. They are generally used in different formulation for enhancement of rheology or viscosity of the material or dispersion. So when we increase or with increase in the shearing stress, the disarranged molecules orient themselves in the direction of flow, because before applying the shearing stress, the molecules are disarranged or randomly arranged, but with increase in the shearing stress, the disarranged molecules of this type of pseudoplastic material, they can orient itself in the direction of flow, and thus reducing the friction and allow a greater rate of shear at each shearing stress. So due to the reduction in the frictional forces between the materials between the molecules, and it allows a greater rate of shear at each shearing stage. Some of the solvent associated with the will be released, resulting in decreased viscosity. And due to the decrement or reduction in the viscosity, this type of flow behavior is also called as shear thinning systems, or this type of liquids are known as shear thinning liquids. So, because of the some of the solvent associated with will be released when this process occur, because initially it was disarranged molecules, but when we apply the shearing stage, they can arrange itself themselves in the direction of flow. So friction will be reduced, and then there will be the greater rate of shear at each shearing stage, and the solvent associated it will be released and decrease the viscosity. Due to the reduction in the viscosity, this type of flow behavior is also called as shear thinning systems. So this is the pseudoplastic system, and when we plot the graph for pseudoplastic system, as we earlier seen, there is the curved graph or curved rheogram for pseudoplastic behavior or pseudoplastic flow, where the rate of shear and shearing stress is not directly proportional. So, in which curve is passing from the origin with zero shear stress, so no yield value is obtained, as we discussed in our plastic system or Bingham bodies, and a shear stress increases, shear rate increases, but not obtain the linearity. So this is the characteristic rheogram for pseudoplastic type of flow behavior of different non-Newtonian systems. So pseudoplastic flow can be explained by long chain molecules of polymers. So polymer long chain with water molecules, where the water is associated with these type of molecules. When we apply the stress, so polymer and water molecule align on direction of force. Storage condition arranged randomly in dispersion. So these are the different pseudoplastic flow. It can be explained by the long chain molecules of different type of polymers. So when we apply the force per area, shear stress, so now applying this force per unit area, shearing stress molecules is like the water and polymer arranged long axis in the direction of force applied, it is seen in our diagram. So this stress reduces internal resistance and solvent molecules released from the polymer molecules, and then reduce the concentration and size of molecules with decrement or decrease in the viscosity value. So these are the mechanism of the pseudoplastic flow, which can be shown by the different type of pseudoplastic systems. So the exponential equation for this type of pseudoplastic system, it can be shown by this equation: f to the power n equal to eta g, where n, capital N, is the number of given exponent. Eta is the viscosity coefficient, which can be generally known as viscosity or pseudoplastic viscosity. In case of pseudoplastic flow, where the value of capital N is greater than 1. So more n is greater than 1, the greater pseudoplastic flow of material. And if when the n value is equal to the 1, the flow behavior will be like the Newtonian. So F will be equal to eta G, and this is the equation for Newtonian liquids. So depending on the number of given exponent, the pseudoplastic behavior can be seen, can be shown by the equation f to the power n equal to eta g, where f is the pseudoplastic viscosity. If n value is equal to the 1, the flow behavior will be the Newtonian behavior. So when we take the logarithm on both sides, n log f equal to log eta plus log g. And when we rearrange this equation, we can obtain a straight line equation like log g equal to capital N log f minus log eta, where g is the rate of shear and f is the shearing stress. Eta is the viscosity. So when we compare with the y equal to mx plus c, which is the straight line equation, we can plot a graph and obtained a straight line with the slope and intercept value. Now, after the discussion of Bingham bodies or plastic behavior, second one is the pseudoplastic systems, and third one is the dilatant flow. So, dilatant flow is the again the third type of non-Newtonian flow, where the liquid or systems do not obey the Newton's law of flow, and we can obtain a characteristic rheogram of where the rate of shear is directly proportional to shearing stress as we obtain in Newtonian liquids. So you can see the characteristic rheogram of dilatant systems, so dilatant flow, where the rate of shear and shearing stress is not proportional or not in the form of linearity, and certain suspensions with a high percentage of dispersed solids are the different examples of this type of dilatant flow. So this type of suspension having the high percentage of dispersed solid exhibit an increase in resistance to flow with increasing rate of shear. Such systems actually increase in volume when sheared and are called as dilatant. So why it is called as dilatant? Because dilatant is expandable. Means such systems actually increase in volume when sheared. So when we apply the shearing force or shearing stress, so they can increase their volume. And it is known as dilatant type of systems, and behavior is known as dilatant flow behavior. So dilatant materials are also known as shear thickening system. When the stress is again removed, a dilatant system returns to its original state of fluidity. So it depends on the stress. So when we apply the stress, they can show there is the increase in the volume when sheared, and they are called as dilatant. But when the stress is removed, a dilatant system returns to its original states of fluidity. So dilatant flow, like the certain suspensions with high percentage of dispersed solid show an increase in resistance to flow with increasing rate of shear. Such systems increase in volume when sheared, and as per the mechanism of increment or expand in the volume, they are called as dilatant flow. So the dilatant flow or dilatant systems are also known as shear thickening system, whereas pseudoplastic systems are a shear thinning system, where the dilatant systems invert to it, they are called as shear thickening system. And when stress is removed, dilatant system returns to its original position. So this is the characteristic rheogram for dilatant flow. So when we plot the rate of shear on y-axis and shearing stress on x-axis, we can obtain the curve or rheogram, and it is just invert to or reverse to pseudoplastic behavior. So in which curve is passing from the origin, zero shear stress, so no yield value is obtained, no non-linear increase in rate of shear, increase resistance to flow on increasing rate of shear. So this is the characteristic features of the rheograms of dilatant flow, in which particles are closely packed with less void spaces. Also, amount of vehicle is sufficient to fill the void volume. So at the resting condition, where the packing system is closely packed system, there is a less void volume, and the vehicle having the sufficient concentration, and the viscosity or consistency is low. So this is the condition at the resting condition, where the after increase in the rate of shear, the closely packed system will convert into open packing system. The void volume is the space between the particles is high, and the insufficient vehicle is there, and this is the high consistency condition. So particles are closely packed with less void space, and amount of vehicle is sufficient to fill the void volume in resting condition, where the particles are openly packed after the applying the or after increasing the rate of shear, where the void volume is higher and the vehicle is insufficient, the consistency is higher. So this leads particles to move relative to one another at low rate of shear. So this is the mechanism or concept of dilatancy. So therefore, dilatant suspensions can be poured from bottle because in these conditions it is fluid. Resting condition, it is in the fluid condition or full fluid state or liquid state. When stress is increased, the particles show the open packing and bulk of the system is increased. Void volume is also increased. So when we apply shearing stress or stress, the particles show the open packing and bulk of the system is increased. But the amount of vehicle is insufficient to fill this void space. So these particles are not weighted or lubricated and develop resistance to flow. And finally, systems show the paste-like consistency, which is known as dilatancy. The behavior is known as dilatant flow behavior, and the systems which show this type of behavior are known as dilatant systems. So because of this type of behavior, the dilatant suspensions can be processed by high-speed mixers, blenders, or mills in manufacturing industries. The exponential equation show this type of dilatant flow, which can be represented like f to the power n is equal to eta g. This is the similar to pseudoplastic equation where the n is the number of given exponent and eta is the viscosity coefficient, which can be represented in poise or centipoise. But in this type of dilatant behavior, dilatant flow, where the n is less than 1 and decrease as the dilatancy increases. And if n value is again 1, the system show the Newtonian nature or Newtonian flow behavior. So it depends on the number of given exponent. If it is less than 1, it decreases as the dilatancy increases, and if n equal to 1, the system again show the behavior of Newtonian liquids. So these are the different types of non-Newtonian liquids, whether it may be like plastic systems, maybe pseudoplastic systems, or maybe dilatant system, as we discussed with the different characteristics, rheograms, and different examples. Now, after it, very important parameter is the thixotropy. So we will discuss the thixotropy in our next lecture in very detail. But for introduction, what is thixotropy? So it can be shown by this rheogram or characteristic rheogram for the thixotropic behavior of some systems. So it is a comparatively slow recovery on standing of a material which lost its consistency through shearing. Thixotropy is only applied to shear thinning systems. This indicates a breakdown of structure or shear thinning which does not reform immediately when the stress is removed or reduced. So when we go through the diagram of thixotropic systems, we can obtain the different hysteresis loops of pseudoplastic systems and for the plastic system. And thixotropic behavior can be simply represented by gel system. Initially, at the resting condition, the system behaves like the gel system. When we apply the shearing stress, it will convert into the sol, and when we again remove the stress, then it will again convert into the gel system. So gel sol system is the very important to show the thixotropic behavior of different non-Newtonian type of liquids. So it is a comparatively slow recovery on standing of a material which can be lost its consistency through the shearing, and the different types of hysteresis loops are the characteristics feature of this type of thixotropic behavior of some substances. So we will discuss this thixotropic behavior in very detail in our next lecture. So these are the different references of today's lecture. You can go through these references and find out the more material regarding our today's discussion. So today's discussion, when we summarize it, it was based on the different types of liquid behaviors or Based on the Newton's law of flow, we can classify the behavior of flow of the liquids in non-Newtonian as well as the Newtonian type of liquids. Non-Newtonian liquids can further classified with the three classes like plastic flow, pseudoplastic flow, and dilatant flow. And different examples or mechanisms or diagrams were discussed in our today's lecture to show the different behavior of non-Newtonian type of liquids. So this was all about the today's lecture. Please go through these references and find out the more material regarding the topic concerned. Now, when we go through the quiz section, you can find some questions here. If shear stress is equal proportional to velocity gradient, fluid is called as. You can go through the reading material and find out the answer of this question. The options are given here: Newtonian fluid, viscous fluid, laminar fluid, or non-Newtonian fluid. Next question is: which of the following represents Newtonian fluids? A is lubricating oils, B is honey, C is rubber suspension, or D is the synthetic oils. So you can go through the examples of Newtonian as well as the non-Newtonian liquids and find out the correct answer for this question. Then rheology is the science of A is the flow of material, B is the particle size, C is the formation of colloids, and D is the formation of complex. Next one is the pseudoplastic flow, is also known as shear thinning system, shear thickening system, elastic deformation, and option B is plastic deformation. So we already discussed in very detail about the pseudoplastic flow. Please go through it and find out the correct option for this question. Next one is the dilatant flow, is also known as shear thinning system, shear thickening system, elastic deformation, and plastic deformation. So what is the dilatant flow? You can pick the correct answer. Next one is the resistance of a liquid to flow is termed as. A is surface tension, B is the viscosity, C option is the density, and D option is microfaradics. So we have to pick the correct option where the resistance of a liquid to flow is termed as. Next one is the concentrated solid suspensions generally exhibit dilatant flow, pseudoplastic flow, plastic flow, or not flows. You have to give the correct answer for this question. Pseudoplastic flow generally exhibited by A option is jellies, B is suspension, C is lotions, and D is the colloids. So you have to go through the reading material and find out the correct answer for this question. The next question is: Bingham bodies are substances which show A is dilatant flow, B is plastic flow, C is pseudo-plastic flow, and D is Newtonian flow. So we already discussed about the Bingham bodies in our today's lecture. Please find the correct option for this question. Next one is the Oswald viscometer, is a type of capillary viscometer. B is used for non-Newtonian liquid. C is type of rotational viscometer. And D option is industrial instrument. You have to take the correct option for this question. The next question is: suspended particles become flocculated in a suspension because A option is particles are closely packed. B is attractive forces between particles are appreciable. C is repulsive forces between particles are appreciable. D is vehicle rigidity.